Okay, I think we're good to go there. We have a good number of people are still rolling in, but we might get started. So, good evening, everyone, and welcome to the first of two November presentations the Water and Environment Society are doing. Just a little bit of housekeeping on this one. The meeting is being recorded. The Q&A session at the end will not be recorded. If you have any questions throughout the presentation, please put them into the Q&A tab, and I'll put them to Terry afterwards, our speaker. So with that, we'll get into it. So welcome everyone again. This presentation is on sustainable drainage systems in water management and wildlife mitigation. We will highlight how SuDS not only provides practical solutions for flood and water management, but also offers significant amenity and ecological benefits, creating a more resilient and thriving natural environment in urban landscapes. We're delighted to have Terry Wilkinson with us today from ACO Technologies. Terry is a specialist design and application engineer. And as a civil engineer, Terry has concentrated his career predominantly in the highways industry, both in his 10 years at ACO and prior to this working as client consultant and contractor for local authority highways for over 10 years. He's a member of the ICE and the CIHT, which is an acronym I don't know. I'll let Terry explain that. And is working towards his chartered engineer status with CPD at the heart of this journey. His professional interests are focused on surface water management and wildlife mitigation and infrastructure, as well as applications including housing, commercial, industrial, and distribution developments. So I will hand you straight over to Terry. Thank you very much, Terry.
Fantastic. Thank you very much for that, David. Thank you for the introduction as well. So yeah, member of ICE, CIHT is Chartered Institution of Highways and Transportation, and ICE as well. So yeah, just a professional organisation there. So yeah, good afternoon, everyone. Thank you very much for joining us today. As David said, today's session will be on looking at SuDS in water management and wildlife mitigation. Thank you for introducing me, so I don't need to do that. Just to say, so I'm from a company called ACO. For those who are not familiar with ACO, we've been around in the UK and Ireland for 40 years. It's our 40th year this year. We're part of the kind of the wider ACO group. We've got ACO companies all across the globe. So whilst we kind of operate independently in terms of UK and Ireland, we can and do sort of delve into the sort of R&D, research development, and a lot of the sort of knowledge that we've got from the wider ACO group. Within ACO UK and Ireland, we're split into two divisions: water management and building drainage. So water management, basically we have kind of external surface water management systems and wildlife mitigation solutions, but we do also have a building drainage division that looks predominantly at internal systems, things like kitchens, wet rooms, that sort of thing, stainless steel, and a lot of bespoke there. But so today I'll be focusing on the water management side of things. And I've got along with me today as well is my colleague Owen Liston. Owen's the I hope I've got your job title right, Owen. You're sales manager for Ireland. So Owen's the kind of the local and regional representative of ACO in Ireland. So hopefully my screen is sharing okay, and you can see that okay. I will hopefully move to the first slide. There we go.
Yep, all working.
Brilliant. Thank you very much. Right, so the agenda that I'll be covering sort of in the next 45 minutes or so. If you've got any questions, please do put them in the chat, and I'll do my best to answer them at the end of the session. If I can't answer them, I will go away and find out for you and come back to you shortly. So the agenda that I want to cover today, I'll start off just briefly looking at the history of SuDS, sustainable drainage systems, and what's driven the need for sustainable management of surface water. Then look at some of the principles and desirable attributes of SuDS design. And then I'll move on to focus more on wildlife mitigation in particular, and what we can do to help enhance sites for biodiversity. And I'll finish up by just looking at a case study or a couple of case studies that demonstrates where some of the sort of mitigation solutions that I've spoken about can be effectively employed and monitored. Important to sort of undertake monitoring these sorts of solutions to make sure that they're effective in achieving what we need them to achieve. So just to kind of start with and sort of summarize really what are SuDS. So SuDS stands for Sustainable Drainage Systems. You'll see the U within it is lowercase. It used to be urban, sustainable urban drainage systems, but the U is now made lowercase, so not just for use in urban applications, but for all types of applications, really. And the main kind of ethos of SuDS is to look at controlling surface water rainfall runoff by controlling the rate and volume of runoff from sites, relieving pressure on downstream networks and sewerage systems, and really trying to mimic as closely as possible natural drainage systems, and sort of deal effectively with treating water as kind of the precious resource that it is, and sort of utilizing all the systems and opportunities that we can at source as well. So I've got an extract up there from the Syria SuDS manual. That's guidance that's been in place for a number of years now. I think the current version of the SuDS manual was published in 2015. And SuDS design and good SuDS design is based on the 4 pillars that are shown there. So we look at water quantity, water quality, amenity, and biodiversity. Historically, when we've looked at and considered drainage systems, water quantity has always been the kind of the big focus, really. So, water is an issue. It's raining, it's landing on our sites. We want to get rid of it as quickly as possible to mitigate against any safety hazards and things like that. Whereas SuDS looks at, actually, as I mentioned, sort of treating water as a resource rather than a threat. So not just dealing with the water quantity, which is, of course, a very important aspect of drainage, but also taking into account looking at the pollution in terms of water quality, how we can provide amenity benefits for the landscapes around us, and designing very much for biodiversity and with biodiversity in mind as well. So kind of just to sort of set the scene, really, just like to sort of highlight the natural water cycle and the effects of urbanization and development over a number of years, and how that impacts in terms of how we think about dealing with rainfall and water. And increased urbanization and impermeable surfaces means that we get less infiltration of water into the ground and into the soil, because we've got these impermeable areas that we're creating and creating more runoff. So lower infiltration, we get less water percolation and flow into the ground, and increased runoff from the surface. Also increases the risk of flash flooding further downstream as well. So the images that I've got on this slide here sort of try to demonstrate that point. And one of the critical elements shown there is the reduction of things like evapotranspiration, where trees and vegetation take water, store water, hold the soil together, providing things like shade and amenity and habitat as well, making it more resilient to climate change and impacts from extreme weather events, which we're obviously seeing more and more of as well. So essentially, we need to try and find a balance with nature, enhance the natural systems around us, and as I say, really try and mimic as closely as possible what happens in the natural state, and treat water and utilize water as that sort of resource. So as I've said, one of the main SuDS principles is that rainfall should be managed at or as closely as possible to where it falls on the ground. So we look at controlling the volumes and rate of runoff effectively, and making sure that we take every opportunity that we can to reuse, infiltrate, evaporate and evapotranspirate as part of that natural water cycle. So looking at things like harvesting water for use on site at a kind of later time has the multiple benefits in terms of reducing the volume of water and potable water demand as well, sort of linked into that. So we really need to look to infiltrate into the ground wherever possible and utilize nature-based solutions to kind of undertake these things. And as you'll see through some of the demonstrations and sort of slides that I go through, as I say, the preference and the first preference is really to look towards nature-based solutions. Often there's a need to kind of integrate that with engineered solutions as well when we've got constraints, particularly in terms of things like the footprint of the site and the scope of what we can fit onto the site. And also when we're looking to protect our natural systems, the use of proprietary treatment systems as well to kind of be used in tandem with them, and to really sort of utilize the benefits of that. It sort of really comes into the sort of the requirements of SuDS as well. And just a few photos on the slide here, just showing a few sort of very simple examples on how some of these sorts of principles can be exploited. And legislation on SuDS varies quite considerably across the UK and Ireland. So just to mention sort of other countries within the UK. So Wales, for example, has had the implementation of Schedule 3 of the Floods and Water Management Act in force since 2019. So they require SuDS to be used on sites of more than 100 square metres on new sites. There's a general requirement in Scotland for SuDS and has been for a number of years. Within Northern Ireland, there's no automatic right anymore to connect to new developments to the existing drainage networks as well. England has kind of sort of fallen or lagging a bit behind some of the other countries in terms of SuDS. It was the start of last year, 2023, when it was announced that implementation of Schedule 3 would be in place within England by 2024. Obviously, we're almost at the end of 2024 now, and we've heard very little about that since. So hopefully that will still happen, but it's looking like it's kind of being moved back a bit as well. So within Ireland, SuDS is required on new developments, except where developers can demonstrate that it's impractical to use them due to sort of site constraints and site circumstances. But we're seeing a number of authorities now in Ireland that include recommendations to incorporate and implement SuDS in new developments. Dublin City Council, Wicklow County Council, just a couple of examples of those. But as I say, I'm starting to see that more and more there as well. So I mentioned about urban areas, and urban areas are becoming even more sort of increasingly built up. And statistically, I think it's something like over 50% of populations now live within city environments. So all this sort of urbanization, population growth, and that sort of thing is having a real detrimental effect and impact on the planet. To put it into, or the land change into context, sort of globally, we've lost somewhere in the region of 46% of forest and tree cover since we started felling trees. And it's estimated that somewhere in the region of 3 trillion trees over the last 13,000 years have been cut down. These are sort of huge figures, and sort of quite hard to kind of contemplate the sort of the scale and complexity of that as well. Through Europe, there's policy for increased tree planting and things like that, albeit it's not a global trend, but we are seeing areas and benefits for that sort of thing as well. And 2021 saw a bit of a kind of a grim milestone where man-made massive things like concrete, bricks, plastics, and all that sort of thing actually outweighed biomass on the planet for the first time as well. And in terms of sort of impacts of construction and what sort of impacts that's had on our biodiversity across the planet, this sort of overview here just gives a kind of an indication of that. So what the graph here shows, what that dotted black line at the bottom there shows, is a kind of background extinction rate. So what would be expected in terms of species extinctions over time if there was no sort of adverse impact from human activity. And you can see sort of certainly within the last 300 years or so, there's been a dramatic rise in terms of species extinctions, due directly linked to the impacts of human construction and that sort of thing as well. Fragmentation is a particularly big issue in terms of species and their ability to kind of move around. Amphibian populations, for example, they'll spend a certain amount of their time within ponds and water areas for breeding and that sort of thing. But outside of those areas, they'll be land-based, and hence they kind of need to move around. So with linear infrastructure like roads, railways, and that sort of thing, it's had a really significant impact in terms of fragmentation, where we've kind of severed the link and the ability to wildlife to move around our kind of networks and our roads and that sort of thing. And this is sort of highlighted quite simplistically here in these images here, but just to kind of demonstrate or highlight what and how we consider in terms of schemes going forward, how we can prevent and mitigate against this. And this is the sort of general principles that are followed in terms of the mitigation hierarchy, which is advocated in most ecological guidance as well. So simplistically put, if we're looking to develop, say, a new development or a new road without kind of considering nature, often that sort of fragments the habitat as shown in picture A there. And that's the sort of thing that we need to avoid when we're looking at new sites, and even when thinking about sort of retrofit and retrospective solutions that we can put on existing sites. So the first thing that we look to do is avoid sort of impact on nature. Often that's not practical or feasible, or there may still be residual impacts from that. So the next kind of step within the hierarchy is then to look at mitigation solutions, shown in picture C there. So that could be things like culverts, underpasses, green bridges, anything that provides sort of connectivity for wildlife to move and cross these sorts of infrastructure and things like that safely. And then as a kind of a last resort, or where there's still residual impacts from development, then we look at compensation, sort of again simplistically shown in picture D there. So compensating for that lost habitat there as well. That can have lots of implications in terms of wildlife as well. But that's the sort of general principles of the mitigation hierarchy that we look to follow. So I've mentioned about sort of decline and that sort of thing, just to sort of highlight a few particular species, particularly in terms of island. So amphibians, the natterjack toad there, for example, amphibian declines are of major conservation concern worldwide. The natterjack toad is one of I think it's the rarest amphibian in Ireland, and it's been listed as an endangered species. There's also been huge declines of hedgehogs within Britain and Europe, and it's estimated that a similar situation is happening within Ireland as well. Curlew there, I've just highlighted there as a bird species that's been particularly impacted. Curlew numbers in Ireland have fallen by around 97% since the 1980s, so huge kind of impacts there as well in terms of biodiversity. And then we've also got sort of implications and impacts on our health. The increasing demand for land is placing a lot of pressure on green spaces, which, as I say, have declined in recent years. So sort of linking this green and blue space or natural capital to our health is a growing field, and it's now very well documented that access to green space and spending time in and around wildlife and nature has really significant positive impacts on our health and well-being. So as I say, evidence shows that sort of living in these environments can promote good health, can aid in recovery from illness and that sort of thing. And people who have better exposure or greater exposure to green spaces have kind of a range of more beneficial physiological benefits as well. So say green environments are really associated or help in terms of our health and well-being as well. And kind of linked to that, there's an economic benefit to that as well in terms of what nature can provide. So not only in terms of health benefits and potential savings on the health system, but also in terms of the positive impacts that can have on biodiversity, creating these habitats and really enhancing what we can and do for nature. So those are sort of some of the issues and drivers, and in terms of what's I say really in terms of driving things like good SuDS design and nature-based solutions and that sort of thing. So just to, as I say, to set the scene, now I kind of want to move on and look at SuDS design principles and their applications as well. So again, sort of coming back to the SuDS manual and highlighting the 4 pillars of SuDS, I just kind of want to cover these kind of each individually within the next sort of 15-20 minutes or so. So the serious SuDS manual that I mentioned, published in 2015, it's a really comprehensive document. It's over 1,000 pages of detailed guidance and advice on everything to do with design, operation, implementation, maintenance of SuDS and sustainable drainage systems, and very much looks at considering all 4 pillars within SuDS as well. So it's a massive topic, so I've had to be quite selective in terms of what I talk about and cover within the next few slides. But hopefully I can give a sort of overview in terms of some of the considerations and design principles that we look at. So first off, I want to start with water quantity. As I say, historically, that's very much what we've always had in mind in terms of when we design our drainage systems. And when we're looking at water quantity, there's two kind of significant options or areas that we can think about when we're thinking about water quantity. So we've got attenuation and infiltration. So attenuation, where we're looking to store, temporarily hold that water during a rainfall event and then gradually releasing it. And then infiltration, where we're trying to sort of mimic nature and infiltrate that water back into the ground. And SuDS hierarchy recommends that we consider infiltration first, so we can assess things like the ground conditions to see if this is possible. We can do this by things like conducting infiltration tests to establish the infiltration coefficient, so how rapidly and quickly the ground is able to absorb and take that water in. And there's tests that you can do there within sort of mentioned in terms of soak away test there and the SuDS manual there as well. So what we do in that instance, we look at the catchment area where the water's falling, design it for appropriate storm periods and storm return periods. So how much rainfall is falling on that area. And then we can establish how much quantity of that water is able to be infiltrated into ground. And from that, we can establish storage volumes required there. In terms of attenuation, similar manner in regard to calculating the volume of the water, so how much is landing on the catchment area. And as I say, this is where the water is held on site, be that through natural systems like swales, detention basins, that sort of thing, or engineered solutions like geocellular systems that can store that there as well. So containing that water or temporarily storing it on site and then gradually releasing it to meet with typically to the natural greenfield response, which tends to be either 2 litres per second per hectare or better, dependent on the requirements for the scheme. And that's something that will be led in terms of the planning requirements for the scheme there. So that's sort of looking at things like geocellular systems, but for natural SuDS features like swales, they can have different parameters when it comes to volume control. So generally they'd be designed for something like the 1 in 30-year storm and have excess flows that then kind of connect into other SuDS features and systems. So as I mentioned, if you're limited in terms of your site constraints, that might tie into maybe a geocellular system that it can feed into that can be installed underground. So dependent on the site and what's appropriate, there's kind of different options, whether that be engineered solutions or nature-based solutions or a mixture of the two. And another consideration when we're looking at water quantity through either infiltration or attenuation is the amount of space that can be stored within the system. So for say like the porosity or the void ratio within the material being used. So to say this is the actual space where water can be stored within the feature. So for things like if we've got stone or non-compressed soil, that might be somewhere in the region of 30% in terms of its capacity within the overall material. Or for something like a geocellular system, it can be up to a maximum, typically around 97% in terms of the storage capability within that as well. So this can become important for sites, as I say, particularly when you've got limited space and what we can fit on and within the site as well. And if we've got low infiltration rates within the ground, then that can be kind of accommodated and calculated for as well. And not all solutions or not all of our designs or systems will be used for just infiltration or just attenuation. You can have a combination of the two. So, for example, you might have a pond with a liner in it that can store up to the 1 in 1 year event, and then to kind of help promote biodiversity and amenity and all the things that I've mentioned already, and then allow infiltration at a higher level than this. So it's permanently got a level of water in it, and then anything above that gets either infiltrated or kind of discharged or connected into a separate system here. So you could have a lined wet swale for, say, the 1 in 30-year event, and then have a geocellular tank above it, sort of similar to what I mentioned a minute ago, with that overflow for extreme events as well. So on the images here, I've got high overflow indicated on the left-hand image there, and say this can be an important feature if we're allowing, say, water to cascade into a tank or something like that in the exceedance event as well. So as well as the sort of nature-based solutions and geocellular systems and things like that, other engineered solutions can also accommodate an element of attenuation within our sites. So, for example, here, high capacity combined curb drainage can offer attenuation benefits. And I've just put an extract up here, which is referenced in Transport Infrastructure Island guidance documentation. And where you're using any system, and particularly kind of attenuation systems within part of the network model, then it's important that we include that system and that component of attenuation as part of the network design. And we can do that using industry standard software. So I just put up there for, say, Causeway Flow, which is a software that kind of I use in this regard, whereby you can model not only the kind of the actual designated attenuation systems, but by modeling the full network, it can provide additional storage within it as part of that. So subsequently, we can potentially then reduce the size of our tanks or other attenuation to kind of utilize that to its full extent. So that's sort of water quantity. Moving on to water quality and thinking about how we manage pollution and what we can do to remove that dependent on the site. So for quality, one of the key drivers, or the key driver, is to remove as much of the pollutants as possible before it's carried forward into either into the drainage system or released into the natural environment. And within the SuDS manual, it splits pollutants down into three categories: total suspended solids (TSS), metals, and hydrocarbons. And just some examples there of where pollution from each of these different types of categories can come from as well, and kind of get washed into our drainage network. So it's important to recognise that acute events can be also initiated by activities like salt spreading. So in the winter on the highway network, we're putting an awful lot of salt onto the roads to prevent ice forming, and obviously, as I say, enters into the wider network. So can be, other things like spillages, whether that be fuel spillages or anything else like that, also need to be taken into account and thought of in terms of our water quality. So as I say, the SuDS manual breaks it down into these three categories here. And then in terms of how we kind of assess that, within the SuDS manual, it's kind of outlined in what they call the simple index approach. So to follow this procedure within the SuDS manual, the first thing that we need to do is look at our site and consider what type of site we've got. And then there's guidance within the SuDS manual in terms of the sort of build up in terms of total suspended solids, metals, and hydrocarbons that you would typically get from these sites. So from sort of the lower pollution sites, as you can see, they're sort of residential roofs, we've got low values of 0.2, 0.2 and 0.05 there. And then going up to the highest sites, or sites with heavy pollution, you can see those values go much higher there. So let's say the first thing to do is to understand the site and what sort of pollution level that we're looking at. And then once we've done that, we can then start to consider and assess what sort of treatment solutions we can employ within that to kind of mitigate and treat against these types of pollutants. And just a few examples on the next couple of slides of some of the things that we can do that. So as I say, one of the core principles of SuDS is that we treat water at source, treat it I'd say as close as possible or at source, whether that be in a kind of an engineered or nature-based solution. In some scenarios, we can allow water to flow over the surface. So, for example, where there's a desire to convey water and where it's not going to impact in terms of safety for things like buildings, risk to people and that sort of thing as well. And that can be an effective means of conveyance of water, or even understanding where that water will go in the higher storm events as well. So an example here of a linear drainage channel system. One of the benefits of this in terms of SuDS is it can keep the inverts high. So the higher that we can keep water for as long as we can, it gives us more scope and opportunity to treat that water at source. So, for example, here, collecting water from say a channel and then discharging it or conveying it into a rain garden or a natural solution like that. As I say, really kind of beneficial in terms of what can be done in terms of SuDS. A slightly different arrangement here with water coming directly into the channel and leading into a green SuDS feature. The overflow on this, in the example sort of shown here, has been set to just below the surfacing layer, and we've got a permeable pipe going into the soil filter medium there. Equally, this could be a pond or other nature-based solution as well. So as I say, we kind of identified the site from the first step in terms of the levels of pollutant. Then we can look at and consider the various SuDS features to treat that. And just some examples here of both proprietary systems on the left and natural systems on the right, in terms of some of the treatment values that these sorts of systems can accommodate. So for nature-based solutions, you can go to the SuDS manual and it will give these values in terms of the mitigation indices. For proprietary systems, sort of the one shown on the left there, go to drainage manufacturers such as ourselves at ACO, and we will provide these for the particular type of treatment system being looked at as well. So as I say, each one can remove a proportion of allocated pollution as well, and it can be used in a kind of as a single feature, or it can be used in a treatment train as well. And often you'll see them designed as treatment trains. So multiple solutions in tandem in order to treat the pollution levels that we've got there as well. And then sort of simplistically how we can look at this in a calculation. So I've got an example site here we've looked at for an HGV lorry park. So this is considered one of the highest level of pollution. So you can see they're 0.8, 0.8 and 0.9 in terms of our TSS metals and hydrocarbons. So then what we do, we can look at our SuDS systems. And in this instance, we'll be looking at kind of putting a treatment train in. So proposing the first system here, a proprietary filtration system. So you can see from the treatment values here, we've got 0.8, 0.8, 0.8. So what that means is that in terms of the TSS, that meets the pollution load there. In terms of the metals, it meets it there as well because of the 0.8. But you can see in terms of hydrocarbons, we've got 0.9 on the site, but it only treats to 0.8 of that. So what we need is a further system in place in this, or a further treatment train to enable treatment of the hydrocarbons as well. So what we're kind of proposing here is taking that into a filtration system, and then the second treatment train there is putting it into a swale. And then you can see there as well that swale has values there in terms of TSS metals and hydrocarbons there as well. The calculation for it, what you do for the first level of treatment, or the first part of the treatment train, you take the full values there, so the 0.8, 0.8, 0.8. But where you've got secondary features, you only allow for half of the mitigation indices of that particular treatment system. And the reason for that is that because we've got multiple, in terms of the first level of treatment, the filtration system there is already kind of removing an amount of pollution within that. So because we have less pollutants in the kind of the further treatment trains, we reduce the mitigation indices by half. So the kind of total in this scenario here, we've got for our TSS, we've got the 0.8 from the filtration system, plus half of the 0.5 value of the swale there, which gives us 1.05. We know that meets the TSS requirement. Similar for the metals. And then for the hydrocarbon, where it didn't meet it just with the filtration system, we take the 0.8 to start with, half of the 0.6 from the swale, which gives us 1.1. So overall, those three values there meet the mitigation requirements within that. So in terms of the systems themselves, that would be a suitable treatment system. We then need to think about sizing it. So that's the kind of the principle of removing the pollutants, but then to make sure that we size the systems appropriately for the required flow rates that we've got as well. So that was looking at quantity and then quality, and then moving on to amenity, sort of how and why we can use water to our benefit to provide amenity, to create and sustain better places for us to live and move around in. Within the SuDS manual, one of the things it says in terms of amenity is that good urban design aims to deliver attractive, pleasant, useful, and above all, livable urban environments. And one of the keys to creating these sort of tangible spaces, for example, is looking at water reuse. We can have seating areas, running routes, things like that. But there's also less tangible spaces with things like visible living walls, green, blue roofs, and that sort of thing as well. So something that can't sort of have that kind of direct, tangible link there as well. So the aspiration of amenity, as I say, is to use water as a resource and help to create these features within the landscapes, and kind of a few options and ideas there, and some of the benefits that can be offered. And ideally, as I mentioned at the start, we want to link this to human health as well. So from, say, talking about the drivers that at the start, mentioned that spending time within these green spaces increases our health, recovery time for illness, and that sort of thing as well. So the creation of these good green blue spaces has a really positive knock-on effect for our health and for the habitats, and acting as I say, a kind of a amenity benefit in that regard as well. And we can utilize things like recreational areas, such as parks and sports fields for not only the purpose that they're there for, but they can so they can be great areas for amenity, but they can also act as good reservoirs for attenuating exceedance events. So when we've got extreme storm events, and you know, in these sort of scenarios where these kind of areas aren't going to be used at that time for what they're designed for, as I say, designing them for exceedance and to take those excess flows temporarily can be a kind of really good solution. So this is just a simple example here of a school site that we worked on a number of years back, where the scheme itself was designed to hold the 1 in 30 year storage volume underground, but in the really extreme events, the 1 in 100 year event, the surface of the playing field was utilised to temporarily store and hold that water as well. So sort of taking the benefits and utilising that in terms of amenity. And then the last of the 4 SuDS pillars is biodiversity. And within the SuDS manual, one of the things it talks about in terms of how we design for biodiversity is the importance of linking habitats. So I mentioned about fragmentation at the start, where we've got roads and linear infrastructure kind of cutting off those migration routes for amphibians. Let's say within the SuDS manual, it says that habitats within SuDS schemes should be designed and provide links with other local and regional habitats, so we can help to enhance and build up that habitat connectivity that may have been lost, or in terms of new developments, preventing that fragmentation, and that can help to mitigate with problems associated with habitat loss within urban areas, and really enhancing our opportunities for our biodiversity to thrive. And SuDS schemes should try to aim to have a range of different habitat types that will encourage all types of biodiversity to help in creating sustaining and resilient ecosystems. And there's various guidance from different authorities, from highway authorities, from local authorities, and a lot of this guidance will follow that mitigation hierarchy that I spoke about at the start, in terms of avoiding those impacts, and then looking to minimise, mitigate, and then as a kind of a last resort to compensate. And a couple of specific documents, one up there from TII and one from NRA as well, in terms of biodiversity design and guidance. And just put an extract up there mentioning about taken from one of those documents that talks about environmental impact statements, and that placement of fauna passages can help to create that path for animals to kind of move safely under and over roads, and create the path for them to move around. And sort of pictured here, I've got a variety of sort of solutions that can be employed to do this. So we've got conveyance by means of wildlife tunnels and culverts. So sort of two or three different examples there. We've got a kind of a sort of a culvert on the left. We've got a wildlife tunnel in the middle of there that's installed very high up, at the road surface. And then the one on the right there, you can see the kind of the entrance just going into the road there, but then it's actually buried under the carriageway itself. So dependent on the things like the species, the size of species, where they're going to and from, would help to determine what the appropriate sort of solution is. And this is where sort of engineers and ecologists really should be working together right from the outset to understand not only the ecological constraints, but also the engineering constraints to provide a solution that works and meets all the requirements for that. And then just on this next slide, I've got a kind of a very brief video of an actual site that incorporated very much these sorts of systems here. So we've got the tunnels there, and we've got also one thing that I didn't mention there is the combined amphibian trap and tunnel there. So that acts as a means of connecting the kind of the guide walls where you've got, say, a sidewall access, but has very large inlets at the top, so it prevents small amphibians from being able to kind of climb over them. So what would happen is that they would fall through into the base of the tunnel there, and then kind of continue on their path via the guide wall. So as I say, just a kind of a simple video showing that particular type of system installed. So we've got a guide wall there, and you can see I think it's kind of every 50 meters or so, we've got a tunnel going under the road. There's that stop channel there, providing that connectivity across between the guide walls, and then another tunnel coming up here as well. So as I say, normally at intervals, and placed and positioned at locations where we know species are and kind of will be moving as well. And just a kind of a nice little video as well to sort of show some of the actual tunnels in use and the sort of different types of species that can use them. So we've got sort of badger at the bottom right there. We've got toads at the bottom left, and it's very hard to see on that one on the top right, but there is just underneath the kind of the sort of the black pipe there. That was actually a site that's recently been installed as a snake tunnel for a site in England where they've got populations of adders separated by a road, and they've recently put this tunnel in as a means to provide that connectivity. So the video capture there actually shows I think it's a grass snake actually using the tunnel, but showing the kind of successful use of these sorts of systems. And then another sort of mitigation that can be very easily either sort of retrofitted or installed in new schemes. We've got an amphibian escape ladder there. So for road gullies where amphibians become trapped in a gully, often with no means of escape, something like this is a simple roll that can be fixed to the sidewall of the gully, and it just allows a means for amphibians to be able to climb out and escape. As you can see, can be very good climbers, and use of these systems can be really effective as well. And then sort of in conjunction with that, we've got a wildlife curb at the bottom there. And these are designed to be placed in front of a gully, as sort of shown in the bottom right-hand image there. They have a recess within them, and how they work is as an amphibian comes up against a vertical wall like a curb, it will follow that line along. It will kind of hug the vertical wall. So as it approaches a gully like that, it will continue to follow that vertical surface. So when it comes to the recess, it will move into the recess, which allows it to sort of safely bypass the gully and come out the other side. So sort of two systems that can be used in tandem there, one as a preventative and one as a means of escape for any that have become trapped. So I've shown sort of guide walls, kind of variations on that. We have like guide fencing. So this is a one-way fence. You can see from its design that it's a curved panel, and as its name suggests, it allows movement in one direction. So from the photograph that you can see there, any amphibians or small animals on the right-hand side of that image were able to kind of traverse over that fence, climb over it, and they would safely drop to the other side. But anything coming from the left of that photo, it will be prevented from accessing it as well. And those can be tied into crossing points as well, underpasses, by means of a sort of a tunnel entrance, which is shown in the sort of the bottom right-hand image there as well. For all diverse ranges of plants and animal species to thrive, we need to create different varieties in terms of landscapes and planting and things like that. And as I say, mentioned within the SuDS manual, it talks about having variety of habitats to incorporate this as well. And we also need to think about the type of environment that they're going to be in terms of the surface water. If they're going to be kind of permanently or very infrequently exposed to water, then we need sort of hardier ones, that hardier plantings that are more able to cope with that. And conversely, for those areas where they're often within or submerged within water, we need to choose the appropriate planting that can work in those sorts of areas as well. So again, that's where the kind of the different disciplines working together. So ecologists and landscape architects choosing the right sort of habitat enhancements and working with engineers to make sure that we can provide solutions that can thrive. So for enhancement of biodiversity using water features, to try and maximise shallow and occasionally inundated areas of pond vegetation. So as I say, areas more resistant to pollution and that can have high ecological value as well. So we look to design systems. So in this example here, where some areas are exposed to every runoff event or fed from separate runoff sources, so lesser polluted areas like runoff from roofs, for example, incorporated into the relevant areas as well. And I just wanted to finish up. I've got a couple of case studies. The first one is a site that's been in for a number of years, and the second one is just a few images of a recent site that the owner and myself have been involved in for a site in Ireland. But the first site that I wanted to show, this is a site in Scotland a few years ago. One of the locks, Frankfield Lock, was part of a wetland park, had a large area of woodland, reed beds and marshland. So the site was a real haven for wildlife habitat and supported a range of species from amphibians and small mammals as well. So from the image on the site there, you can see sort of the new housing estate shown in that sort of dotted red line there. And the road that connected that housing estate to the main road development cut across that path between the lock on the left and the marshland on the right. So what was proposed here, this was sort of designed at the early stages between ecologists and engineers. So the ecologists understanding the species that we had on site, where they're moving to and from, and so choosing correct locations for underpasses. So shown on 1, 2, 3 there on the plan, we've got 3 tunnels going under the road, and then that blue line providing a connecting feature in terms of guide fencing to connect between the tunnels and also extending beyond them as well to provide as far a scope as possible in terms of funneling the wildlife into the tunnels there as well. So say 3 tunnels were selected there, about 100 meters in length along that road, or spread over 100 meters, so 50 meters apart, and then another 50 meters of the guide wall either side of that. And this particular image is just a photo, so you can see the lock in the background there and one of the tunnels shown crossing the road there. And you can also see part of the fencing within that photo as well. And I put up some values there in terms of monitoring. So it's really important that we monitor these solutions to make sure that, say, they're effective and they're doing what we set out for them to do and what we want them to do. And with really encouraging results from the monitoring this. So we had cameras, or there were cameras installed within the tunnels to monitor the different types of species. And you can see we've got toads, frogs and newts there, and the different values in terms of which direction they were moving as well. So as I say, really kind of encouraging to see these sorts of solutions being used. We also supported a student from Nottingham Trent University at the time who was doing a lot of work on hedgehogs and how and where they kind of move around. And she actually did some monitoring on that site that I've just been shown there as well, which actually showed some really encouraging results in terms of hedgehogs using the tunnels. And she kindly sent these couple of videos through as well that she was able to capture while she was doing the monitoring. So although they weren't designed with hedgehogs in mind, it's great that other species are using them, and particularly with hedgehogs, as I say, their numbers being in kind of quite stark decline as well. And then the last one, this is a site, as I said, Owen, I've got, if you won't mind me putting up there, I've got a photo of Owen on the site there. This is a new housing development that's currently underway just outside of Dublin. one of the largest part of one of the largest housing projects in decades to be undertaken there. And the tunnel that's just been installed there is one of the first of 3 proposed on the site, and it was being required to support safe movement and protection of amphibians on the site that rely on watercourses and water bodies in and around the area, so being able to kind of move around the area. So you can see these ones from the surface. They're slotted top units, and the slots on the top basically allow light and moisture into the tunnel to help encourage the use of amphibians using them as well. They're made from polymer concrete material, which has many benefits in terms of drainage, but it also has a big benefit in terms of amphibians. Polymer concrete is not subject to the same residue buildups that you can get on sort of standard cement concrete, which can actually be toxic and fatal to amphibians. So a very appropriate use of material for that as well. And I've just shown at the bottom there a sketch of the kind of layout, an indicative sketch to kind of show the levels and that passing through the kind of the curbs and the footway and making that connectivity there as well. So that is pretty much it from in terms of the presentation. Got my contact details up there and Owen's contact details up there as well. So